Okay, so today is the fourth day of the course, and really today we will discuss grid integrated wind energy conversion system. So there are so many electrical machines, right? You have studied in your undergraduation. You have squirrel cage induction motor, wound rotor induction motor, and then doubly fed induction generator you might have, and PMSG and synchronous electric motors. There are so many different types of machines which can be used for wind integration. But as you can see here, first we will see the wind energy highlights. Okay. Then basically we will discuss a little bit about PMSG based wind energy conversion systems, and then doubly fed induction generator based wind energy conversion systems and the problems related with diffig machine. If you have the series compensation, so we did some work in collaboration with Hydro-Quebec and IREC and those things. And then some standards and grid codes. All those standards and grid codes I will discuss in the second half of the lecture from 12 o'clock to 1:30 also. That then I will discuss IEEE standard 1547 also. So wind energy highlights. See, world's largest onshore wind farm. This is Gansu wind farm in China. Initially, around 10 years ago, I heard about it, and they were saying that it will be 20 gigawatt. But now we don't know how many. So I found out that it's around presently 8 gigawatt or so. And there are some problems. So I was in China for 2-3 weeks. I was visiting and discussing with some researchers. So they have some management problem in the farm, and it has to be transported, the energy has to be transported at long distance, then wind problem, and then there is another problem in China. That problem is of instability, voltage instability. So I was in China, I was discussing with their research big lab. They have hundreds of researchers are working, and then I visited many universities. So this is the problem. This is the problem, that when you integrate too much renewable energy, intermittent energy with the system, then it becomes a problem. Okay, so that I will discuss a little bit tomorrow also. But they have the voltage instability problem. Voltage instability caused by the intermittence nature of the renewable energy. So so I was talking there, and then because you know the objective of global net zero is 2050. United Nations, they have conferences and those COP21, COP26, 29, and I think COP30 took place recently. So this is what we are discussing, that by 2050 we should have global net zero. Whatever we are emitting greenhouse gases, those should be absorbed. So global net is zero for by 2050. This is what we were discussing. But so this is what I was discussing in China. But China has clearly said, no, they cannot reach that objective. So they have extended it to 2060. And why? Because this is the problem, voltage instability problem. They have so much renewable energy that now the system, they have voltage instability, and because of that, till 2030, they are focusing on thermal power plants. See, so the focus is a little bit shifted now to make the grid stable. So I will talk about this sometimes. So this is the thing. In China, perhaps they had initial problems, so that's why they are not going very strictly following that, okay, we have to reach 20 gigawatt, because they already have so much renewable energy. So this is what it is. So in this Gansu wind farm, 7,000 wind turbines with DFIG machines, doubly fed induction generator, from various manufacturers, Goldwing, United Power, Vestas, and 2,383 kilometers of HVDC transmission line. And there they have the mismanagement and those things. So this is what I came to know. But still it is the largest wind farm. Largest onshore wind farm in USA, Alta Wind Energy Center. So it has 1547 megawatt installed capacity, and they have Vestas wind turbine, 3 megawatt wind turbines, V90. I think 90 is perhaps the related with the, all the time I think about the French word, blades. In French we call it pal, so I was thinking pal, but blades, wind turbine blades, serving the needs of this much Californian home. Then, as far as I know, largest onshore wind farm in India, perhaps it is Muppandal wind farm in Tamil Nadu, 1500 megawatt installed capacity with 3000 turbines, ranging in size from 200 kilowatt to 1650 kilowatt, from Enercon and other, Suzlon also, and Vestas. Perhaps what I think, why they have different sizes of wind turbine, perhaps it was developed in different stages, perhaps because of that. Earlier it was not that a fashion to put very large, so perhaps they started with 200 kilowatt. This is what I think, that now with the development of technology, this is what is happening. Largest offshore wind farm, Hornsea 2 offshore wind farm in North Sea, UK. 1.32 gigawatt installed capacity with 165 Siemens Gamesa 8 megawatt wind turbines. And it is operational since August 2022. There are many other offshore wind farms under construction, like Dogger Bank Wind Farm. It is situated over 130 kilometers of northeast coast of England in North Sea. When completed in 2026, Dogger Bank will be the largest offshore wind farm in the world with an installed capacity of 3.6 gigawatt with Heliad X 13 megawatt turbines. Then Greater Shingwa offshore wind farm. This project involves 4 wind farms, Changwa 1, Changwa 2A, 2B, 4, located 35 to 60 kilometers of Changwa contained Taiwan, with total capacity of 2.4 gigawatt. Changwa 1 and 2A were commissioned on April 25, 2024, and the other 2 will be commissioned in 2026. So these are ongoing projects. So this is a picture of offshore wind farm. And then tourism is also taking place with the wind farm, like in Vancouver, Canada, we have this 1.5 megawatt wind turbine to have an observation pod. Okay, and then in Bahrain, you have World Trade Center, this tower with three wind turbines completed in 2008. Okay, so 225 kilowatt wind turbine is supplying 50% of the building power consumption. Then Strata Towers, 42-story skyscraper with 3 built-in wind turbines at the top. Okay. And then if you see the wind turbine, Siemens SWT7154 wind turbine, 7 megawatt. It has 7 megawatt rated, very large size, medium speed PMSG machine, 75 meter blades. Okay, the equivalent of 9 double-decker London buses, and swept area, you can believe it, this much swept area. Then Vestas V64 wind turbine, 8 megawatt rated power, medium speed PMSG. So all these large sizes basically are PMSG machine. 80 meter blades, equivalent of 9, okay, swept area. Okay, and nacelle, 24 meter long, 12 meter wide, 7.5 meter high, weighing approximately 390 tons. So can you believe how difficult it is to build? And then Vestas, another turbine, 10 megawatt. Okay, rotor diameter, see, 80 meter blades. Each blade weighs 35 tons. This is the swept area. And then Heliad, this 13 megawatt, 107 meter blade, 13 megawatt. Okay, 248 meter high. Siemens Gamesa, 14 megawatt, world's most powerful offshore wind turbine. It was available, but I don't know who is using, if they have enough order for that, it's difficult to say. So world's largest wind turbine, Dongfeng Electric, 26 megawatt. I think it is still under construction, and because some companies, they announce in advance so that for future they are assured, okay, whoever is building wind, offshore wind farms, so they should keep this in mind that this machine will be available. So, and then Mianyang Smart Energy, 16 megawatt capacity, and another, I don't know what is this thing, 50 megawatt, but people want to get the publicity also. So now coming to the PMSG based wind energy conversion system. So what are the features of permanent magnet synchronous generator based directly driven wind energy conversion system? One important thing is the elimination of gearbox, because gearbox is always a problem. Almost 10% of energy is wasted in gearbox. Can you believe? 10% of energy is wasted in gearbox. And the maintenance of gearbox is not that easy. Okay, all the time, after 2-3 years, there may be a leakage of oil and those things. So you have to send, by helicopter, you have to send a person to go on the top of the turbine to fix. So it's not that easy. So that is the maintenance problem, because it is the rotating part. So some wear and tear in the rotating part. So those are the problems with the elimination of gearbox. Okay, so if you remove the gearbox, what are the consequences? You use gearbox to increase the speed of the generator, because you have seen the blades are slowly moving like this, like maybe 15 or 20 turns per minute, right? But your generator has to run fast to generate 50 hertz or 60 hertz. So if you don't have gearbox, how will you increase the speed? You know the formula. N is equal to what? 120 F by P, right? This is the basic formula, right? So if you have lower speed, so it means you have, to get 50 hertz or 60 hertz, you have to increase the number of poles, because you are rotating with slow speed. So you have to increase the number of poles. So suppose you have 4 poles running at 1800 RPM, generating 60 hertz or so, but then your speed is not more anymore 1800 or something like this. It may be much slower because there is no gearbox, right? So it means you have to increase the number of poles. So instead of having 4 pole or 8 pole, you have to have 80 pole or 100 pole or something like this, right? To have the same frequency, 50 hertz or 60 hertz, right? So if you increase the number of poles, then the diameter of the rotor will increase. So this is what is happening. Enercon has developed annular generator type PMSGs. They have the large diameter to accommodate even 100 poles or more than 100 poles. That depends what is the capacity of the machine. So the diameter, so there is the advantage. So if it is rotating with slow speed, it means very low wear and tear, so less maintenance, less losses. But I don't know about the cost. Perhaps it may cost more or something. That cost basically depend how many machine you are ordering. If you are ordering 5 or 10 machines, the price may be different. If you order 100 machines, the price will be different. So it basically depends on this thing. So, right? So elimination of a gearbox. Then there is a work going on magnetic gears also. One of my colleagues is working on magnetic gears. So, but that is a costly thing. So you cannot put it on wind turbine. It will be very costly thing. So at that scale, 8 megawatt, 10 megawatt scale magnetic gear. So you have limited choice. You have to increase the number of poles if you don't want gearbox. Then variable speed operation for MPPT. This is available if you have PMSG machine. You can have variable speed operation and you can extract maximum power. You can do MPPT algorithm and extract maximum power from the machine. No slip rings and brushes. This is a big advantage. This is permanent magnet machines. Now when we talk about permanent magnet has problems, and you know the problem. What happened in trade war recently? So Trump said, okay, 142% tariff on China goods. China said, okay, I am increasing 250%. See? And can you believe? Within a month, Trump came to the table. Why? Because they need rare earth materials. And I tell you, more than 90% of rare earth material is processed in China. So nobody can fight with China. All is controlled by China. If you want permanent magnets or other rare earth material, so you have to go to China. You don't have any, because it's not a simple work processing the rare earth. It pollutes the environment and contaminate people. So not every country will want to do. And then after that, when this happened, so Trump came to the table, everything was solved. Okay, so tariffs came down, everything came down with China. And with India, they were, oh, you are buying Russian oil, and then we have to increase the tariff of 50%. And what about China? You were fighting with China for so many years, and then now you are blaming India that you are buying Russian oil. And I tell you, US is buying so much uranium from Russia. They don't see this thing. But anyway, this is not our topic. But what I want to say that in 2011, I was doing one project with a company TM4. Now it is, they call it Dana TM4 in collaboration with Hydro-Quebec. And they produce powertrain for PMSM, electric vehicle. So in 2011, we had one project with them, and the engineer was saying it is so frustrating. At that time, 14, 15 years ago, it is so frustrating. Permanent magnet prices have increased 7 times in 1 year. In 1 year, the prices of permanent, perhaps China might be having some policy at the time, I don't know. So it was very frustrating for those companies which are making powertrain, because the cost of permanent magnet will increase. And then there was one company, Molycorp, and it was listed in NASDAQ, and then prices of shares of Molycorp were increasing because they was working on permanent magnet or rare earth material. And then suddenly in 2015, it crashed. Molycorp shares crashed. Perhaps something might have happened. China might have given some statement or something. And now perhaps it is bought by some other company. But anyway, this is the thing. The China may control based on rare earth material, and permanent magnet is one of them. So they control more than 90% worldwide market on this thing. And then PMSG has enhanced fault right-through capability. Low voltage right-through, high voltage right-through, or fault or some. So it has capability. Why it has capability? Because you have full size back-to-back converters. To converter, they totally decouple the generator from the grid. So that's why it has that fault right-through capability. And then reduce copper losses due to use of permanent magnet. In rotor, you have permanent magnet, not any winding or those things. High power density, depends what kind of material permanent magnet you have used. So these are the things which makes PMSG more efficient and reliable. So this is the thing about this. Now this is the basic control, grid connected. Here you have a grid, you have PMSG, this is wind turbine, back to back full size converter. So if you say you have 10 megawatt generator PMSG, then you need 10 megawatt this converter and 10 megawatt this converter, which may be a very costly. On the first thing is that machine itself is very costly, but you know, we always talk about, okay, permanent magnet machine is costly, but do you know how much, if you say the whole wind turbine, how much it will cost after all, the generator? So I was reading one article, so they said 20% of the cost of whole wind turbine is the towers. So what you make the towers? Another 20% comes to the blades. Okay, and if you come to the generator, it is 8 or 10% of the total cost. So generator is not that costly related to towers and blades and those things. But anyway, still you have full size converters, back-to-back converters, and then you have controller. This converter you can use to extract maximum power. So MPPT will be done on these things, right, using some kind of control. There are so many MPPT control techniques, perturbation, observation, and other things. So extract power from here and bring it to the DC bus. So if you are not extracting power from DC bus, the dangerous situation may arise. The voltage may keep rising because energy is being pushed into the capacitor, DC link. So you have to extract that energy and send it to the grid, and that is the work of this converter. So it is basically the same type of thing which we have seen in active filters yesterday and before yesterday. What active filter? We have said that one objective of shunt active filter is to keep the DC link voltage constant. So how it will keep the DC link voltage constant? It will transfer the power from DC link to the grid. And then on top of that, this converter may work as a filter also, a power conditioner also. So this is what I tell all my students. Okay, you have converter, inverter, they are not loaded all the time to their full capacity. Most of the time they are loaded up to 50% or so. So what you are going to do with the rest of the capacity of inverter, converter you have in the system? That capacity you can use for reactive power compensation, for harmonic mitigation, for load balancing, like power quality system. So basically, this inverter from DC AC, this is an inverter you are pushing, so that is fine, you are pushing the energy to the grid using this inverter, but at the same time it should work as a power quality conditioner also. So we integrate all the time, yeah.
Sorry, inverter और grid के बीच में कोई filter नहीं है?
What?
Filter.
Filter?
Inverter और grid.
No, this is, I have shown you a simple diagram. This is just a simple presenter. Otherwise, you will have the coupling inductor, filters, and those things. Just to show a basic principle, this is what is going on.
Other signal conditioning devices may be there.
Yeah. Well, always coupling inductor, capacitor, those things are there, filtering. But basically this inverter, suppose there is a load here, non-linear load. So what I wanted to say, that if it is a non-linear, unbalanced, reactive load, then instead of providing those harmonics or reactive power from the grid, why don't you use this inverter to compensate those problems? So this is why, so apart from transferring energy from the DC bus to the grid, the another, because it is not loaded fully most of the time, so the same converter inverter, you can integrate those aspects in this. Apart from, you have, certainly you have coupling devices, yeah. So this is this generator side converter control. It means this converter. We are talking about generator side. So if you see here, so this is the power speed, this is output power, and this is the generator speed. This purple color, this is for mechanical power. Whatever power is produced, the wind is coming and the blades are rotating, so that mechanical power is going at the shaft, so that mechanical power. But the electrical power generated is not that much because there are rotation losses and other things. So basically, for extracting maximum power, we use this curve, blue curves we have to use, not the purple curves. Okay. So from power speed characteristic, the maximum power at different wind velocity is almost a cubic function. So this is what we are seeing. This is the cubic function of generator. This curve is utilized to obtain torque command. So suppose we say, okay, this much power, this is the maximum power point. So you see on this curve, if we put a curve here, maximum power point, so basically this will be the reference generator speed, and then you can measure the actual speed, okay, and then you have PI regulator, so it is giving the reference torque, electric torque, reference electric torque you can calculate based on how much power. So you don't have to do calculation all the time. The MPPT, you can even use just this curve, okay, and for particular turbine, because you see different speed, 12 meter per second here, 10 meter, so curves are different, 8 meter per second, 6 meter, 4 meter per second. At different speed, you will have different maximum power, so reference speed has to be changed. So that reference speed you may calculate using this curve, and this is the measured rotor speed, and this is PI controller, and this is the reference electric torque. Now for electric torque, basically this is the equation for this machine, and he see D axis inductance, Q axis inductance. But if we consider the cylindrical rotor, in cylindrical rotor LD is equal to LQ. So basically this term will be 0. So finally you will have this and this portion. So that's how, if you say we have reference electrical torque here and you know all these values, so you can calculate reference Q axis current which is proportional to the electric torque. So electric torque is proportional to basically the Q axis current, not the D axis current, Q axis current. So on the generator side, IQ is more important, and on the grid side, ID will be more important. So here we are talking about IQ, and you can set ID current to be 0 so that you can minimize the losses and maximize the torque. Okay. Now coming to the control of, okay, again generator side converter. So this is what PMSG, grid side converter. So you measure DC link voltage, you measure DC link current, IDC, VDC, multiply both, this will give you the output power. So this is the power basically which is coming to the DC link, voltage multiplied by current, that is the power here. So that power, then you use this curve which is the topmost point of for each wind speed, where you draw this cubic curve, and from there P, whatever P is there, then corresponding reference speed, right? This is the reference speed here, or for this reference speed may be different. And then you measure the actual speed, and then you calculate, this is the PI and this is the electric torque using this equation. So electric torque, once your reference electric torque is calculated, using this term you can calculate IQ reference, and you can put ID reference as 0. Okay, and because you have measured the speed, you can integrate this, and this will give you theta angle. So then you can do DQ to ABC transformation. ID, IQ are there. You can get IA reference, IB reference, IC reference, and you can measure the actual current and you can generate the signal. So this is the control, the simplest control. Otherwise you may get very complicated control and those things, there is no limit to make. This is just to explain, okay, this is the basic idea of this thing. Okay. Now if we talk about the grid side converter control, and you will be surprised and happy to know that you can almost use the same algorithm, basic algorithm which we use for shunt active filters, because there also the same things are there, right? So this is what we did in shunt active filter also. We had the reference DC link voltage, measured DC link voltage, PI control, and it will give you the amplitude reference of the current. And then, like yesterday professor was saying, okay, you are using unit this template and there is a problem in unit template, the voltage is distorted. Right, you are right, so that is the right way. But then, because it is a very simple control, this is otherwise you can use PLL and those things to get perfect sinusoidal, right? So you have unit vector, this unit voltage vector, measured voltage divided by this Vt, and it will give you sine omega t minus 1, like same thing we saw in shunt active filter, sine omega t plus 120. Okay, so this is UA, UB, UC, you multiply it by this and you get IA reference, IB reference, IC reference. So very simple control. and you can put it like this. Like same thing as in active shunt filter, we are putting the same thing. You are measuring this VA, VB, VC, calculating the unit vector for the voltage UA, UB, UC. Okay, you are measuring 3 grid currents IA, IB, IC, and here you see you have measured VDC here, you have reference VDC, PI controller. So this is the amplitude of the grid current, and you multiply it with the unit vector. This will give you IA reference, IB reference, IC reference, which are coming to hysteresis or PWM control, and you are measured current, and then you can generate the signal for grid side converter. So what is basically happening? You are trying to keep the VDC constant. So how you will keep the VDC constant? Because from the other side, power is constantly being shifted to the DC link, and your objective is to keep VDC link voltage constant. So power will be transferred from DC link to the grid automatically. And at the same time, your grid current, these are the reference and these are the actual, they will be kept sinusoidal. Automatically, all the harmonics, which might be, suppose there is a load here, non-linear load, which is generating, which is non-linear load, harmonics are there. So it will automatically compensate, this control will automatically compensate for the harmonics or voltage unbalance, this current unbalance, not voltage, current unbalance and those things. So if you see the total thing together, so this is for grid side control converter, and this is for, no, this is for generator side. Generator is here, here it is grid, this is the grid side converter, and we have just put it together. Now there are lot of results and those things, just to show that this is the speed in RPM of generator at that time. Your speed is increased, so you see the current of the generator, they are increased and frequency is increased. This is VDC, this is grid voltage, which is constant and sinusoidal all the time. Okay, this is the load is 2 kilowatt. So why actually the student put 2 kilowatt load? Because he wanted to implement in the lab. So in the lab we were having 2 kilowatt machine. And then you see the speed is increased. So the power initially generated by the inverter supplied by the 500 watt, but because the speed is increased, so power output of transferred became almost 1500. So the grid will provide less power to the load. So this is what to show. The grid current earlier was this, now the grid current is reduced because the power was coming from the turbine, wind turbine. Okay, this is just to show these results. And there are some other results. And then just to show that wind speed is changing, so generator speed is changing, voltage and current of generator is changing. And it is just to show that this is the grid voltage, constant sinusoidal voltage, and this is the grid current, and this is the load current. Until unless this grid side converter was not started, your grid current was same as the load current. But as soon as grid side converter started, it started doing the harmonic elimination, reactive power. So that's why the grid current become sinusoidal and less, because power is coming. See, apart from the fundamental component of the current coming from the inverter, you have harmonics also. So fundamental component, it will put more grid current. So this is what it is. So what you can do, you have the wind turbine or PVs, you can connect to the DC link of the inverter. Okay, and it is the same inverter. Basically, if you have a shunt active filter, and if you want to integrate your PV or grid power, you connect at the DC link. The only thing is that you will have to increase the capacity of IGBTs which you are using, because extra power is being transferred to the grid. So the size of the IGBTs will increase. So you see, this is what the student has done. This is the 4-leg grid interphasing inverter. This is the grid. This is the 3-phase 4-wire nonlinear load. So you are measuring VDC, reference VDC, error, and then a student has used NFIS, adaptive neurophysical inference system, some kind of adaptive control he has used to generate ED reference. EQ reference is 0 to have unity power factor. Okay, and then DQ to ABC currents, and neutral current reference is 0 because you want to compensate neutral current on the grid also. Okay, you have measured VAB, BVC, and then you have measured the 4 currents here, and then the control for this is produced. So what was happening was that in 2003, that came this IEEE standard 1547 came in 2003, and we were so much not happy about this, because almost at the same time we started working, because earlier we were working on this power quality thing and active filters and those things, and then I realized, okay, that area is becoming saturated now 20 years ago. So you have to divert your attention, you have to remain active, you have to show that something new you are working, right? So we started applying the same technique which developed for power quality inverter to the renewable energy integration. So at that time, more than 20 years ago, we started working on this renewable energy integration. And then at the same time, this 2003 IEEE standard 1547 came. So initially we were happy, okay, some standards are there to integrate distributed renewable energy sources and those things. There at the time, I think they were calling it variable energy sources or some other term they were using instead of DER, they were using some other term. And then in those 1547 IEEE standard at that time, they said, okay, as soon as any disturbance comes on the grid, you have to disconnect. You have to disconnect your PV, you have to disconnect your wind turbine. What is this? This was all nonsense. So we were fighting in IEEE on those things. Why you are putting those things like this? Because those are generating power. If you need some frequency assistance or load assistance, they should be helpful to you. And instead of helping, you are disconnecting them. And this is what it was there in 2003. I will discuss that after the break. I will discuss about IEEE standard 1547. So we were not happy. At that time, we were working. And see, this is what is happening here. These renewable energy sources were supposed to supply only active power. They should not touch the reactive power. They should not touch the harmonics or any other thing, right? This is what actually the voltage sag, voltage swell, those things, you are not concerned about this. They were told to the wind farm operator, okay, disconnect your wind turbine, disconnect your PV. And so what was happening, that this renewable energy sources were supplying only the active power. So if you have a load which needs active power, harmonics, reactive load. So everything was coming from the grid. That was the problem. Now what was happening? That if load is there, your renewable energy sources was providing only the active power. So all the reactive power, harmonics, those were compensated by the grid. So grid became polluted. That was the problem. Grid became polluted because all the harmonics are coming. So what is the use of having such a good quality inverter there? You have an inverter there. Why don't you use that inverter used in the renewable energy? So this is what the work we did. And we were fighting for this all the time. And then we suggested at that time, long ago we suggested this thing, and that was the effect that in, I think, 2018, when the new IEEE standard 1547 came, then they integrated those things what we were suggesting 10 years ago. Okay, so here you see, this is the grid, this is the load. Load needs active power, harmonic power, reactive power. So, because the inverter, interphasing inverter used with PV and wind turbine, which was already loaded, only loaded up to 50% or 60% of the capacity, it was just lying there, that capacity. So we used that capacity not only to transfer active power, but to compensate harmonics and reactive power also, so that the grid became less polluted. So this was the very pioneering work we did many years ago, and finally the fruits came, and in the form of new IEEE, updated IEEE standard 1547. So we will continue with our discussion, and we were discussing the control, and these are the simulation results. Okay, so you can see grid voltage is perfectly sinusoidal and of constant amplitude. But if you see the load current, it is highly nonlinear, unbalanced nonlinear current. And this is the inverter current. So what is the objective of this inverter? That it is fine that it is whatever energy is generated by PMSG, it is being injected into the grid. So this is one thing. So here you see this current is of inverter is unbalanced and some harmonics are there. This is to compensate this thing. So it is, this current is generated in such a fashion that grid current is perfectly sinusoidal. And if you see here, you will see that it is in phase opposition of this voltage. Okay, it means the current of the generator is being pushed into the grid. So voltage and current in phase opposition means the power is going inside the grid. See this very interesting result. This blue is the grid voltage, and ILA, red one, this is the phase A of the load current. And you see IA is the grid current, blue. So you see this current is in phase opposition of the grid voltage. It means it is not a load, it is the current power generated and pushed into the grid. Okay, and this is the load current, and inverter current, you see the green is the inverter current. Why it is non-linear? Because it is taking care of the harmonics. So that's why it is cancelling all the harmonics, plus it is giving the fundamental component of the current. You see the line neutral current, this one is the neutral current of the grid, and this is the inverter current, this one. inverter neutral current. So it is cancelling the grid neutral current, load neutral current. So if you see the grid neutral current is zero, because load neutral current is being cancelled by the inverter neutral current. So it is compensating for zero sequence current also. So student did the experimentation work also, and here you see the grid currents. These are highly nonlinear. It is just to show active filtering mode of 3-phase 4-wire nonlinear unbalanced load compensation by the grid side converter. So as soon as grid side converter is put on, all these non-linear grid currents, they become sinusoidal constant current. And these are the inverter currents of phase A, B, C and the neutral current. So if you see this portion here, it is shown here. So see, because it is cancelling the harmonics and pushing so this is the current injected by the inverter. This is inverter in wind power injection mode with 3-phase 4-wire nonlinear unbalanced load compensation simultaneously. So simultaneously it is injecting power as well as doing the filtering also, inverter. So this is the grid voltage of phase A, grid current phase A, load current phase A, inverter current phase A. So if you see, explain it here, this is the grid volt phase A, which is constant sinusoidal. This is the grid current for phase A. It is because inverter current of phase A is injecting the extra current. So that's why in this part grid current is reduced, because extra current is coming from the inverter. So the load current is constant. And here also you see grid voltage and current, load current, inverter current. And if you expand this portion here, this is the grid voltage, this is the grid current. Before the starting of grid inverter, grid current were distorted. But as soon as you started putting, it becomes sinusoidal and in phase with this thing. Now speed and position sensorless control of PMSG. Earlier we had measured the speed and those things. Now we are talking about sensorless control of PMSG. Precise information about rotor speed, position is essentially required for the vector control of PMSG, right? Generally shaft mounted speed and position sensor, as you might have done in your laboratory. Use of sensors may result increased cost and complexity, time bound maintenance, tearing and wearing of mechanical parts and connected lead, false operation of sudden breakdown. So these are the problems if we are using mechanical sensors for position and speed. So to alleviate the need of sensors, several speed and position estimation algorithms have been given. So there are many more other algorithms which may compensate and where you need not to use speed and position sensors. You estimate those things. Speed and position estimation may suffer because it may have some problems also in estimation. Ignorance of parameter variation, rapidly changing weather and operating conditions, distortion in current and voltage signals, inaccuracy involved in low voltage. So there are many problems. But this adaptive neurofuzzy inference system technique developed by a student, it has certain advantages. So this is what actually sensorless control of PMSG was done. So you are not measuring position or speed of the generator. You are just measuring the voltage and currents. Even the students said, okay, we can avoid the use of third current sensor because the sum of all the current are zero and voltages and current are zero. So then VA, VB, VC, you have IA, IB, YC, and then you have ABC2 alpha beta Clark's transformation to, actually it should be voltage alpha and voltage beta. It should be current alpha, current beta. And then he used ENFIS system control algorithm for position and speed estimation. So position and speed estimation was done. So on the DC link, so this is grid, this is generator side control. Okay, so you are measuring VDC, IDC, which is giving you power at the DC link. So you use this for MPPT, which will give you, which we have already discussed, reference speed. This is estimated speed. Using PI controller, it will give you IQ reference. ID reference should be 0 as we had discussed before. And then DQ to ABC transformation. And here reference current for phase ABC. And these are the measured current. So this is how you generate the signal using PWM. And then those are the, I think I have less time, so I should speed up. So this is the error in speed estimation. The student did small errors while the ramp is there and position was okay. And then these are hardware implementation. So I will speed up, I will not explain those things. Now coming to doubly fed induction wind energy conversion system. So as basically a double wound induction, on the rotor side you have winding, on the stator side you have winding. Stator you are directly connecting to the grid here. This is the wind turbine and the gearbox. This is a gearbox. Actually DFIG machines in my home province of Quebec in 2007 they started putting the wind farms and they started using doubly fed induction generator by the General Electric Company, and its capacity I think was at the time 1.5 megawatt machines. And then they were using 500 kilowatt rotor side converters, these. So if you are saying this is 1.5 megawatt, this is 500 kilowatt. So this is the advantage, the cost is reduced. First of all, DFIG machine is cheaper than PMSG. Another thing, the inverter, this is 1/3 capacity, variable speed range is from this, gearbox is there, bidirectional back-to-back converter, okay. So what are the overall advantages of DFIG fed wind energy conversion system? Reduced converter cost, as the converter rating is typically 25 to 30% of total system power rating. Improved efficiency due to reduced losses in power electronic converters. Suitable for high power applications. Bidirection flow of reactive power. High fault ride through capability during network disturbances. And flexible 4-quadrant operation with precise control. This is the advantage of DFIG based wind energy conversion system. So if you compare this DFIG, PMSG, so this is what actually we call it wind energy exploitation technologies. So there are type A, type B, type C and type D. Type A is basically squirrel cage induction generator based converters, this wind energy, that is type A. because if you are not using full size inverter converter, then it is difficult to do the MPPT. Then you have type B with wound rotor variable resistance machine. This is again induction machine.